The last thing I'd like to talk about is some mapping properties of fractional linear transformations. We're going to see that fractional linear transformations take lines or circles and map them to lines or circles. So there's an easier version of that becomes true almost by definition. So let me present you that version first. So let me define RP1 first of all, and this is just similar to CP1 with everything replaced by real numbers. So I have T and S inside CP1, but I'm going to restrict them to be real numbers. And so this is what I'll call RP1, and I view it as sitting inside of CP1. And so this is really just the real line inside of C, but I'm also adjoining the point infinity. Now, a line in CP1, I'll keep that in quotes, is just something of the following form. So it's where I fix a matrix in GL2C, and I take A times elements of R2 except 0. And this really amounts to taking the FLT FA and getting the image of RP1. And you can think of this as you're sort of like taking combinations of the columns of A, even though we don't exactly have a linear structure on CP1. But this is what we'll call a line in CP1. And from this definition, we get just a very easy fact that fractional linear transformations map lines in CP1 to lines in CP1 because a line in CP1 is already written as FA of RP1. And so if I have another one of these, FB, and I compose, well, there's not much to say here because we know that the composition of these just multiplies the matrices. So FB maps this line in CP1 to this line in CP1. So this result is no big deal. But what we really want to do is dig into what are lines in CP1. And they are what I said they were. Lines in CP1 are in direct correspondence with a line in C union the point at infinity, or just a circle in C. And what's the correspondence? Well, you take the projection of a line in CP1, so it'll have a bunch of points of the form Z1, Z2, and for the points that aren't infinity, I can project to Z1 over Z2 in C. So this is when Z2 is non-zero. And I claim that a line in CP1 will project to one of these two objects, and vice versa. If I have a line in C and I union it with infinity, that will be a line in CP1, or I can view a circle in the complex plane as a line in CP1. First, let's explain how we go this direction. So if we have a line in C union infinity, why is that a line in CP1? So here we go. If I have a line in C, that can be written as points of the following form, where I have A and B complex numbers. I guess you would want A to be non-zero. A would give the line a direction, and B would translate it. So this is a line in C, and I claim that if you throw in infinity, you would get exactly this set. Well, this looks pretty close to it, but it's not exactly the same. So the points I've written here are AT plus BS over S. But when S is non-zero, this is equivalent to AT over S plus B. And so this would project exactly 2 points in the line that we started with. So every point here that's not infinity is a point on our line, and every point on our line is a point of this form, because you replace t here with t over s. And we also get infinity thrown in, because that's the case where s equals 0. Now let's show that every circle in the plane can be written as a line in CP1. So we do this in steps. This is basically based off using the inverse Cayley transform. So if I start with the unit circle, one can show that you can represent the unit circle using these points if you project them to the complex plane inside of CP1. So the points we have here get written as t minus is and t plus is. And since both t and s can't be 0 at the same time, the second component is never 0 in this setup. So I could convert this always to how we write points in the complex plane. And I'll leave out some of the details, but this number here will have modulus 1. And you can show every number of modulus 1 can be written in this form. I'll leave some of those details out, but the unit circle can be written this way, basically parameterized by rp1. And then if you want the circle of radius r, you just dilate things by the factor of r. And if you want the general case of the circle of radius r and center a, well, we take our earlier case and we translate it using one of these elementary matrices. So we get every circle in the plane represented as a line in CP1. Now the last thing to show is that every line in CP1 is one of these. So I claim it is enough to show that translations, multiplications, and inversions send lines and circles to lines and circles. Why is that? Well, the way this starts out is lines in CP1 are the image under an FLT of RP1, which we've already said is R union infinity. So again, reviewing R as a subset of C here. So certainly this is the x-axis, so that's a line. And I want to show that any FLT will send a line to a line or a circle. And since every fractional linear transformation is a combination of translations, multiplications, and inversions, I just have to check it for each of these cases. So certainly a translation sends a line to a line, and a multiplication sends a line to a line. There's not too much to check there, so I'll leave that to you. You do have something to check with inversions, so this is part of an exercise. So exercise, this will be in the homework, show inversion maps lines to lines or circles. Okay, next we need to check that, so although we start out with a line here, we need to show that, a line may get mapped to a circle, perhaps through an inversion in here. So we would also need to check that our 3 types of FLTs send circles to lines or circles. And again, it's clear that translations send circles to circles and multiplications send circles to circles. The only thing really to check is that inversion sends circles to either lines or circles. So that's also part of the exercise. So circles map to lines or circles. So this here is the technical heart of everything. It's kind of a technical exercise. It's not terribly difficult, but it's not that exciting to watch, so that's why it's left as an exercise. But this establishes that every line in CP1, which starts out basically as RP1, which is basically the real line, well, gets mapped through a bunch of translations, multiplications, and inversions to either a line or a circle. And that shows that every line in CP1 is a line or a circle when you restrict to the complex plane, and we've already shown the opposite direction. So that covers everything.